Very nice welcome to the Indian farmer, Aravartiyan Krisak and Bhartiya Hindustani Kisan quantum physics classes. And today we are going to talk about the Schrodinger equations. So let's start Schrodinger equation. We have seen that a macroscopic particle is essentially represented by a matter wave with its wavelength given by the de Broglie relation. We also describe the motion of such a particle or a system of such particle. Clearly, we cannot make use of Newton's laws of motion for this purpose, so a new theoretical description is needed for the motion of quantum mechanical particles. The new theory should be consistent with the wave nature of particles. It should also reduce to Newtonian mechanics for macroscopic particles. This condition is similar to the special theory of relativity, which reduces to Newtonian mechanics at velocities much smaller than the velocity of light. In, in this connection, we like to discuss a event at the end of a seminar in 1926 on de Broglie waves. The physicist Peter Debye said to another physicist that if matter is a wave, then should be a wave equation to describe matter wave. Debye promptly forgot, forgot about it, but the other physicist, Erwin Schrödinger, proceeded to discover the wave equation for matter waves, and this equation is named after him as the Schrödinger equations. So see the Schrödinger equation. We have already learned that wave nature is an inherent property of every particle. We now need a wave equation which suitably describes the time evolution of matter waves representing the particle. We have learned that one way of localizing a particle is by constructing a wave packet. However, uh, we have also seen that a wave packet spreads with time. This means that a wave packet cannot represent a particle. Hence, in quantum physics, it is postulated that every particle or a system of particles is represented by a wave function which is a function of a space coordinate and time. The wave, the wave function determines all that can be known about the system it represents, and this is known as first postulate of quantum physics or first postulates of quantum physics or description of the system. So for a one-dimensional motion of a particle, the wave function may be represented by psi x comma t. Here psi x comma t means this represents a single term. X and t represent, that is the function of x and t, the space and time. Also you can write only psi. So what is the form of psi x comma t in terms of x and t? To answer this question, consider a classical macroscopic particle moving under the influence of a force. Its dynamical behavior is described by Newton's second law, which is a differential equation. Similarly, Maxwell equation of classical electromagnetism are also differential equations. Since all objects exhibit particle as well as wave nature, it is natural to expect that the quantum mechanical wave function will also be a solution of certain differential equation involving derivatives of x and t. Derivatives of x and t. The credit for discovering such a differential equation goes to Erwin Schrödinger. Erwin Schrödinger And how did he arrive at this equation? The answer is he created it intuitively breaking all tradition of such wave equation. The Schrodinger equation is one of the most successful equation of quantum physics because it predicts result which can be verified experimentally. So let's discuss the Schrodinger equation. Let's first state certain preconditions for establishing this equation. Firstly, for a particle of mass m and energy E and the momentum P, momentum P, the equation should be consistent with first the de Broglie relation equals to lambda by h by p, equation 1, and the second Planck's formula or Planck's relation nu equal to E by h or E equals to h nu, and third it can also satisfy the relation E equals to p square by 2m plus v x comma t, total energy equals to kinetic energy plus potential energy of a particle. So, and finally the Schrodinger equation must be linear in x and t. This is the fourth condition. That is, if psi 1 x comma t and psi 2 x comma t are two solutions of the Schrodinger equation for a given potential energy V x comma t, then any linear combination of psi 1 and psi 2, say C1 psi 1 plus C2 psi 2, with C1 and C2 as arbitrary constant, must also be the solution of the same equation, same Schrodinger equation. This linearity is required that two waves must be added to produce interference. If the linear property to be satisfied, the Schrodinger differential equation must be of degree 2, that is the wave function, and its derivative appearing it should be of the first power. Now, using equation 1 and 2, using equation 1 and 2, in 3 we obtain h nu equals to h square 2m into lambda square plus vx comma 2, or h omega by 2 pi equals to h square by 2m into 2 pi by k to the whole square plus vx comma 2, or finally we get h cut omega equals to h cut square k square by 2m plus vx comma t, this is equation 4, where omega is equal to 2 pi nu and k, 2 pi by lambda. Now we consider a simple situation where the particle energy is constant, say equal to v naught, equal to v naught. Under such a situation, if we take the particle to be a photon, then it will have a fixed wavelength and frequency, and its wave function as given by the electromagnetic theory should be psi x comma t equals to a into e to the power I kx minus omega t. This is equation 5. So differentiating the above equation once with respect to time, we can obtain once with time and twice with a space, we can obtain del psi by del t equals to minus I omega psi x comma t, or equals to omega psi x comma t by I, or this gives omega is equal to I by psi into del psi by del t. This is equation 6. And twice differentiation with respect to x or a space, we get del 2 psi by del x square equals to minus k square psi x comma t, and this gives k square equals to minus 1 by psi x comma t del 2 psi by del x square. Sorry, this will be del x square. So using this equation 5 and 6 in 4, we get I h cut del psi x by t del psi by del t, I h cut del psi by del t equals to minus h cut square by 2m into del 2 psi by del x square plus vx comma t psi x comma t. This is equation 8. The above equation has been obtained for a special case of constant potential energy V naught. However, Schrödinger made a bold extrapolation and postulated that the form of equation 8 does not change even for a particle of mass m moving in a potential which varies with space and time, that is x and time, x and t. Thus the time dependent